Welcome to ClockFabric Electronics Academy. Here we will study electronics and computation from an inventor's perspective. In this video, we will show how to create, compile, and program a new project in Quartus Prime Lite edition and explore the software's most prominent features and tools along the way. We will use Intel Cyclone 10 LP FPGA Evaluation Kit as our reference board, but with careful modification, the steps shown in this video should apply to other similar evaluation kits using Intel's FPGAs as well. My name is Bard, and I'll be the host for this video presentation. Intel Quartus Prime Software Suite is Intel's official FPGA development platform. It provides everything needed to design systems for Intel's FPGAs, SoCs, and CPLDs. The Lite edition, which can be downloaded for free without a license, is what we have installed for this presentation. We have shown how Quartus Prime Lite edition can be installed in our previous video titled Installing Quartus Prime Lite 17.1 and the board test system. Let's start this video by launching the Quartus Prime Lite software by double-clicking the shortcut that we have very conveniently placed in our desktop. So the software opens with a very non-cluttered interface. A closer look reveals that the main interface has been divided into 7 distinct panels. The first one is the main menu bar with 9 drop-down menus: File, Edit, View, Project, Assignments, Processing, Tools, Window, and Help. We are not going to go through each and every one of them right now. We would rather come back to them as we create a project and manipulate its settings. The second panel is the main toolbar that provides shortcuts to the most commonly used tools and features as icons. This panel is fully customizable so that we can put our favorite tools here for easy access. The next distinctive panel is the Project Navigator. The Project Navigator offers 5 different project views. There are hierarchy, files, design units, IP components, and revisions. These settings offer a unique perspective on our project. For now, let's leave it as it is. We will come back to it later when we have a project and its files to navigate through. The fourth panel provides a list of tasks that the Quartus Prime software will perform on a project for a project to be successfully loaded into the FPGA device. The Tasks panel provides 5 distinctive views of the tasks. They are compilation, full design, gate level simulation, RTL simulation, and rapid recompile. We will just leave it at compilation for now. The Messages panel is the 5th panel in our main interface. This panel will display the output messages being produced by the currently running tasks as we move through the compilation process. There are these message filters that could be applied to the messages to isolate the messages based on their priorities. For example, if we click on this warning message filter, this panel will display only the warning messages. The 6th panel is the IP catalog. This panel is used to browse through currently available IPs from Intel and Altera for a particular device. It also gives us an option to search for partner IPs in the internet. IPs are components prefabricated for reuse in our projects. The device family lists the name of the devices that these IPs can be used with. In this case, Cyclone 10 LP is shown here. That means these IPs listed here can be used with a Cyclone 10 LP FPGA device. We will see how IPs are imported and used in our project later. Finally, in the middle, we have our 7th and the last panel. Right now, this panel is showcasing the home screen, which lists important shortcuts like New Project Wizard and Open Project. It also lists web shortcuts to Intel's website like documentations, trainings, and support. Later, when we start editing our project files, this is where the text and schematic editors will appear. We will refer to this panel as the main panel for future reference. To make pointing out to the panels easier, Intel has tagged almost all of them with unique names like Messages, IP Catalog, Project Navigator, and so forth. So in the future, if we mention a panel with a name, the easiest way to find it is to look for its tag. Apart from the name tags, these panels exhibit one really cool behavior. They can be moved around and docked at our preferred site. This allows the Quartus Prime's interface to be fully customizable. At this point, we are done with the introduction of the first user interface. Now let's move on and create our first project. So the new project can be created by initializing the new project wizard, and there are two methods of initializing the new project wizard. The first method is to just click on this new project wizard button present on this start screen. The second and most commonly used method is to go to the File menu and click on this New Project Wizard link. As we can see, the New Project Wizard window that pops up lists of 5 steps that this wizard is going to perform in order to create a new project. Let's just click the Next button and give this project a name. But first, we will have to assign a working directory for this project, so that our project files can be organized in a single folder and moved around if need be. Intel recommends creating a new folder every time you create a new project so that the settings files can be isolated from various projects we might be working with at the same time. So let's just do that. The next step is to give our project its name. We recommend using the same name that the directory was given. It just makes project management a whole lot easier in the long run. Now we need to give a name to the top level design entity for this project. It is somewhat like giving a name to the file that contains the main function in C or C++. This top-level design entity is what is manipulated by the compiler later, and everything else is called by this top-level entity for further compilation. So for those coming from a software programming background, the similarity between the main function and the top-level entity might seem pretty obvious. Once again, we recommend giving the top-level design entity the same name as the project and the top-level directory. Even though reusing the same name is not necessary, it just makes things a lot easier. Now let's move on to the next step. In this step, we can choose to either create an empty project or use an existing design template. Design templates are prefabricated projects with all the settings preset so that we can modify them a little bit here and there to meet our design goals. These design templates could prove to be a lifesaver at times, but for now we are just going to go with an empty project here and click Next. In this step, we can choose to add various design or settings files to our current project. Right now we don't have any such files, so we will just click Next here. Okay, so this step is probably the most important step in this whole project creation process. Here we get to choose the FPGA device that we'll be developing our designs for. First thing you notice is that there are 2 tabs at the top left of this window, Device and Board. The Board tab doesn't seem to be functional at this time, so we'll just stick to the Device tab here. Under the device family, we'll select Cyclone and LP and set the pin count to 256. Then we will resize the window a little bit and locate our device from the list of available devices. Make sure that the name of the device matches the name of the device present on our board and click Next. Here we can specify other EDA tools which can be used with the Quartus Prime software for synthesis and simulation. For example, if we are planning to use third-party simulation tools like Model Sim from Mentor Graphics, then we will mention it here. But since we are not planning to use any third-party EDA tools for this project, we will just leave it blank and click Next. Finally, the new project wizard generates a summary of all our settings based on which our new project will be created. It's always a good idea to go through it briefly and make sure all the settings have been made correctly and then click Finish to generate a new project. After a few seconds, the new project will be created, and the user interface will change drastically. The first thing we notice is that previously disabled menu items have now been enabled, and the project navigator has this new entity listed with our project name on it. The task panel also has all its tasks enabled now. Before we start with the project files creation, let's set the global settings for the project so that we can focus solely on our design related tasks later. It's always a good idea to set the global settings before we move on with the project and start manipulating the project files. Quartus Prime Lite 17.1 provides these 4 main global settings that we will review and change before we move on with the project. The first global setting is selecting the FPGA device itself. This is going to be the device that we'll be working with throughout the project lifecycle. The device selection can be done by browsing to the Assignments menu and then clicking on this device link. This will bring forward the same window that we used to select the device when we created this project. Since we have already made our device selection, we will just review our selection and press OK. The second global settings page can be accessed by browsing to the Assignment menu and clicking on this settings link. A settings window will pop up which will allow us to go through a lot of project-wide settings. Let's go through them one by one and at least have a general idea of their existence so that we can come back to them later if we ever need them. The first one on this list is the general settings. Here we can select the top level entity file for this project. Right now we don't have any files in our project, so we will just leave it as it is. The second one lets us add other design files into our project so they can be included in our project compilation hierarchy. The third one lets us include libraries. These libraries would contain user-defined or vendor-supplied mega functions, block symbol files, and or other HDL files for reuse in our project. The fourth one lets us change settings related to our IP catalog and search locations. For now, we're not going to make any changes here. The fifth one lets us add design templates into our project. The sixth one lets us select device power characteristics, including voltage and junction temperature settings. We will come back to these settings later when we deal with power management options. In the seventh settings tabs, we see this compilation process settings. Here we can choose to enable or disable parallel compilation and declare how many processors we would like to use for our parallel compilation process. In our case, we have 8 processor cores in this computer, so we will just let parallel compilation process use 6 out of them. This is important because when we are working with really complex designs, we don't want our whole operating system to freeze for hours. So if we limit our processor usage, then we will have a chance to do something else while the compilation is being done. At this point, we recommend that our viewers experiment with these settings and figure out what works for them. For now, we will also select this Use Smart Compilation and run I/O assignments analysis before compilation settings. One more thing to note in this panel is this output directory name. This is the directory where our output files will be located. These output files are the files that we will need to program into our FPGA later using the programmer. Since our Lite edition does not support incremental compilation, we'll just skip that for now. Incremental compilation is a notable feature that allows hierarchical and team-based designs only available with a paid license. The 8th settings panel lets us specify other EDA tools that we would like to use with our projects for design entry and synthesis, simulation and board level timing and other settings. This is the same window we saw while our project was being created using the new project wizard. The 9th settings panel involves compiler optimization mode and HDL compiler versions. We will leave them as they are for now. The 10th settings panel lets us choose the synopsis design constraint or SDC file that will be used by the TimeQuest timing analyzer for timing analysis. We will come back to this page later in this video when we specify the timing constraints to our design for verification. The rest of the settings panels allow us to change settings for the assembler, design assistant, signal tap logic analyzer interface, power analyzer settings, and simultaneous switching noise or SSN analyzer. We will come back to them later when we need them. Saying that, we are done with this settings page for now. Let's click apply and then OK to get out of this page. Now let's move on to the third global settings page. It can be accessed via the tools menu as a customized link. In this pop-up window, we can actually customize the icons that are present in our toolbar. We will leave it to our viewers to customize the toolbar as they see fit. Now let's move on to the fourth and final global settings page. It can be accessed via the tools menu through this options link. These options lets us customize our IDE and select fonts and things like that. It also lets us manage our license and proxy server settings, which some users might find useful. There are these two features that we could not help but notice. The first one is this notifications feature. This feature lets Quartus Prime notify us when the compilation is complete. Like we mentioned before, sometimes when you're working with really complex designs, it might take a very long time. So this feature lets us perform other tasks while the compilation process is being done. The other user-friendly feature is that we can actually use third-party text editors as our preferred text editor to edit our HDL code. But we'll be using the default Quartus Prime text editor, which meets all our current requirements. So let's leave these settings as it is and click OK to close this option space. Since we have reviewed all the global settings, let's come back to our project creation process. The first thing that this project needs is a top-level design entity file. Like we mentioned before, this is the main file that the compiler deals with. The top-level file can be a block diagram or schematic file, a QC system file, a state machine file, a tickle script file, an ED file, or any one of many HDL code files. For this example, we'll create a block diagram or schematic file and save it as the top-level design entity file. There are several ways of adding a new file to our project. It can be done by clicking on the New File shortcut present on the toolbar or by navigating to the new link present in the File menu. From the New File dialog, let's choose a block diagram/schematic file and press OK. The new file is named as block1.bdf by default. We need to save this file as a top-level entity to register it as a top-level design entity file. So let's just do that by clicking on the Save As link in the File menu. The Save As dialog box will recommend a file name that is the same as the name of the project. This is important for the project to recognize this file as the top-level entity file. Now we can just click Save and close this dialog box. This top-level entity file could very well have been a Verilog HDL file. Later, when we will introduce Verilog, we'll repeat this process by creating a Verilog code file as a top-level entity file. At this point, our project creation process is complete. Now we can start editing this schematic file by adding some components to it. Before we add components to our schematic, we would like to discuss what we're building for this example. For this example, we have decided to create a counter with one clock input and assign the LEDs present on this board to various counter bits so that we can observe the counter bits counting on the real board. Let's try to visualize what we mean by that. So we are taking 150 MHz clock signal as input and 4 user LEDs present on the board as output. We will then import a PLL from our IP catalog to divide our 50 MHz clock by 50 and generate a clock signal of 1 MHz. That 1 MHz clock will then be fed into a 32-bit counter, which can also be imported from the IP catalog. We'll then connect a 32-bit bus to those counter bits. Finally, we will connect the LEDs to selected pins from within the bus. But since the LEDs are inverse logic, meaning they glow when the logic is low, let's just add a NOT gate between the bus pins and the LEDs so that they will glow when the bit is high. This example has become like the hello world of FPGA design process. So let's just stick to this very simple design as our first project. Now let's just repeat what we just visualized in the Quartus Prime schematic editor and synthesize our design. Once again, there are several different ways of adding a component to the schematics. One way is to click on the symbol icon present on the schematic editor toolbar. The schematic editor toolbar has several other icons present on it. Let's have a quick overview of them before we proceed. The first icon allows us to detach the schematic editor from the main window. So if we have a multiple screen setup, we can easily move the schematic editor to a separate monitor and work with it there. The second icon, which looks like a mouse cursor, is the selection tool. The third one is the zoom in and out tool. The fourth one is the pan tool. The fifth one allows us to add text to our schematic. The sixth one is the symbol tool that we discussed before, which allows us to add a symbol or a component to our design. The seventh one is a shortcut to adding pins, which can also be accessed through the symbol tool. It allows us to add input, output, and bidirectional pins to our design. The seventh one allows us to add a custom block component to our design. We will come back to this one later when we start designing custom blocks for our project. The eighth one is the orthogonal node tool. It allows us to add a single node-to-node connection between our components. The ninth one is the orthogonal bus tool. It allows us to create a bus and add multi-node to node connections between our components. The 10th one is the orthogonal conduit tool. The 3 icons that follow are the diagonal versions of the orthogonal node, orthogonal bus, and orthogonal conduit tools. Moving on, the next 4 icons allows us to add shapes to our designs, including a rectangle, ellipse, straight line, and an arc. These 2 icons are more like features that apply to the other design tools. The first one enables or disables use of parcel line selection, and the second one enables or disables use of rubber banding. Rubber banding is a neat feature that allows connected components to stay connected while they are being moved around. The rest of the icons are self-explanatory, like save, print, and so forth. After this quick review of the schematic editor toolbar, let's come back to adding a component. Another very convenient way of adding a component to our design is by just double-clicking at any blank space within our design, like this. The cursor has to be in the selection mode for this to work. Once we are in the Add Symbol window, we will have to browse through all the available components and find the one we need. Right now, we are going to add an input pin to our design, so let's find the pin from within our components libraries. The input pin must be in the primitive section, so let's expand it. Once again, let's expand the pin section. Here we go. Now let's select the input pin. Once selected, we also notice a visual preview in the preview window. It looks like that's exactly what we need. Let's click OK and close this Add Symbol window. Now we can place the pin wherever we want in our schematic editor. One thing to note here is that we could have added that pin by clicking on this Add Pin tool icon also. Now let's give this pin a name. Let's call this CLK50 because it is going to bring in a 50 MHz clock input to our design. There are 2 ways to assign a name to our components. One straightforward way is to just double-click on the name field within the component. The other way is to right-click on the component and click on the Properties link. This will open a Component Properties window. In this case, it is called a Pin Properties window. As we can see, this window gives us access to all the properties of the component. A name can be assigned by editing this name field over here. We can also assign default value to this pin like VCC or ground. Now let's add the output pins or LEDs to our design. Let's use the Add Pin tool this time. We will need 4 output pins for this design. Since the schematic editor is granulated, we can actually use the granules to properly space our components. Now let's assign some names to these LEDs. The schematic editor makes it really easy to name similar components in a sequence by hopping from one component to another like this. Now we are done with the input and output pins. Let's import a PLL module using the IP catalog. Since the IP catalog offers a search function, we could simply search for the component we want by typing out the name in the search bar. All the Altera IP components are prefixed with ALT. So this alt PLL is what we want for our design. Let's just double click on it to customize it for our use. Since we are creating a variation of the PLL module that Altera offers, we will need to give a name to the variation that will be used in our design. A variation will be imported to our project in the form of an HDL file, which can be one of these VHDL or Verilog files. Let's select Verilog for our example and call it PLL0150. This is just a naming convention we have adopted to use. A 01 is used so that it won't conflict with other PLLs that we might use in our design. And 50 is here to remind us that we are going to use a clock divider of 50 for this particular PLL module. Now let's click OK and start customizing our component. All of the IPs will use this MegaWizard plugin manager for customization. Every component has their own versions of MegaWizard interface. On the top right, we can see the steps involved in the customization process. As we can see, this PLL module requires 5 distinct steps. So let's go through them one by one and create the variation we require. The first thing we notice is that we need to provide the input clock frequency value here, which is 50 MHz in this case. We can leave everything else as it is for now. We do recommend our viewers to go through them quickly as some of them might apply to their particular design in a later time. Now let's click Next. Here we need to make some changes. we're not using a reset input to asynchronously reset the PLL, so we can disable it. And we are not using a locked output, so we will just disable that as well. As we can see, the preview of our component updates dynamically as we make changes in this interface. Now let's click Next. Here we can leave everything as it is and click Next. Since we are not using a second input clock for a clock switch over, we don't need to make any changes here. So we will just click Next. Here also we're not making any changes, so we'll just click Next. Now here we need to make some changes. This is where we assign values to our clock multiplier and clock dividers for our clock output. These settings apply only for the first clock output C0. Let's set the value of clock divider as 50 and click Next. The PLL modules present in our device, that is Intel Cyclone and LP FPGA, supports 5 clock outputs. So if we decide to use other clock outputs from this particular PLL module, then it should be done here. And we would set the clock properties to all those individual clock outputs one by one. For this example, we're just using one clock output, so we can just click Next here and for other 4 clocks as well. In this step, we can choose to use other third-party simulation libraries to simulate the generated design files. Altera Mega Function simulation library is added by default, and we will leave it as it is. This page also allows us to generate a netlist for this component, which will later be added to our project's netlist. We will just generate a netlist later when we compile our project all together. So we will leave this field here unchecked as it is. Finally, in the summary page, we need to decide what kind of files we want this Mega Wizard to generate for us to import into our project. For this example, we will just create a Quartus Prime symbol file which we will import to our design file later. Now we are done with this Mega Wizard. We can click Finish and close this wizard. What follows are mandatory steps to notify us that we're using Intel and Altera's IPs in our project. They are kind of watermarked, and this dialog is asking us if we are okay with it or not. We will just say yes and move on. Now we are done with our IP variation generation process. To import our newly created component, we'll once again go to Add Component and find it. Let's do that by double-clicking at a blank space on our design file. In the list of libraries, we can see this newly added field called Project. When we expand it, we will see our newly created PLL module. Now we can simply click on it, review it in the preview window, click OK, and then we can place it wherever we want in our schematic editor. We will place it right next to our input clock pin. Now we can connect the input clock pin to the PLL module's input clock by drawing a wire between them by using an orthogonal node tool from here. Now let's import a counter module using the IP catalog once again. Let's start by searching for counter in the IP catalog. We find this counter module named LPM counter. This is what we need for our project. Let's double click on it and start customizing it using Mega Wizard just like we did for the PLL module. Once again, since we are creating a variation of the IP, we will need to give it a custom name. Let's call it counter0132, since we are creating a 32-bit counter. The Mega Wizard interface that opens up lists only 3 steps required to customize the counter module. Let's go through them quickly. In the first step, we will need to declare how wide we want our counter to be. For this example, we'll create a 32-bit wide counter, so let's set it to 32 here. The counter direction could be set by selecting one of these settings. We want our counter to be up counting only and then click Next. In this step, we won't make any changes and click Next. Same here, click Next. Similar to while creating the PLL module, we will leave it as it is and click Next. Finally, we'll select Generate a Quartus Prime symbol file and click Finish. Once again, we will agree to this IP from our vendor to be watermarked and click Yes. Now let's go find our newly created component, add it to our schematic editor. Let's use an orthogonal node tool to connect the clock output from our PLL module to the clock input in our 32-bit counter. But this time, let's use the schematic editor's built-in smart functionality to connect the nodes. While in selection tool mode, if we hover over a node, we can see our cursor change into an orthogonal node tool. Now we can simply click and drag a wire to the other node that we want to connect, just like that. At this point, our counter is ready to be used, but in order to access the bits within the counter, we will need to attach a 32-bit bus to it and assign a name to these bus pins. Let's attach a bus pin to the counter by using the orthogonal bus tool present in the schematic editor toolbar. And then go back to the selection tool and right-click on the bus, click on the properties to give it a proper name. This step involves a quirky little trick here to give this bus a proper name. So a bus, by its nature, has an array of elements, which can be represented in HDL by using this square bracket notation as shown on the screen. This notation also shows how we want our bits to be arranged. So if we had it set like 0 to 31, then the bits would be arranged in reverse. For now, let's just set it as 31 to 0. Now we can access any bits from within the bus as a pin, which can be linked to any node for logic manipulation. Before we link the bus pins and the LED output pins, let's attach a NOT gate to our output pins. Once again, we will need to use the add symbol tool and locate the NOT gate. A NOT gate can be found in primitives under the logic category. Since we are adding 4 NOT gates to our design, we can select this repeat insert mode so that we can keep adding components until we are done, and click OK. When we are done adding our desired number of components, we can simply press the escape key on our keyboard or click on the selection tool to get out of the repeat insert mode. Now let's connect the output of the NOT gates to the respective LED's inputs. Finally, we can now link the bus pins coming out of the counter to the inputs of the NOT gates. But in order to access the input of the NOT gate, we'll need to extend it using an orthogonal node tool. We will just draw a node and leave it hanging a little bit away from the NOT gate, like this. Now we can assign each node a bus pin's name to link them together. That way they will carry the same logic. It's like they have some kind of invisible wire connecting them, so let's just do that. We can change the names of the instances of the symbols present in the design by double-clicking on the inst label like this. This step is not mandatory for small designs, but in a complex design scenario, these instance names might play a very important role in documentation and collaboration. At this point, we're done with our schematic design. Now all we need to do is analysis and elaboration of our design before moving forward. We can analyze our designs by browsing into the processing menu and expanding the Start category and clicking on the Start Analysis and Elaboration link. When we run this task, we can see a lot of messages being produced in our Messages panel and a compilation report being generated at the main panel. This is a common behavior of Quartus Prime whenever it is performing a task. Now if we look at the task panel, we can see a green check mark next to Analysis and Elaboration task. This suggests that this task has been successfully performed. We could have run the Analysis and Elaboration task by simply double-clicking on this task here also. Now if we scroll down to the bottom of the Messages window, we can actually see the final outcome of this Analysis and Elaboration process. In our case, we got this message saying Quartus Prime analysis and elaboration was successful, 0 errors, 0 warnings. This process of going through the output messages and verifying whether everything went well or not is a very important step in FPGA development. So developing this habit of analyzing the output messages and taking care of all avoidable errors and warnings is what is going to make us a successful FPGA developer. Since we did not get any error at this step, now we can move on to the next step of assigning real pins to the input and output pins present in our design. The pin assignment can be done by using the Pin Planner tool, which can be found under the Assignment menu or from the main toolbar as this icon. Let's just click on this icon and open the Pin Planner for now. So the Pin Planner window opens a separate window by default. If we look closely, the Pin Planner window also has this Detach Window button. If we click on it, we can actually reattach the Pin Planner window to the Quartus Prime software's main interface. We can work like this to have a unified interface, or we could detach the window for more real estate. We will just leave it detached for a better view this time. The pin planner window interface looks similar to the Quartus Prime main interface. It consists of 7 panels. The first panel is the main menu bar with 7 drop-down menus that are File, Edit, View, Processing, Tools, Window, and Help. Like before, we're not going to go through each and every one of them right now. We will come back to them later whenever we'll need them. The second panel is the main toolbar, which is placed vertically by default. It can easily be moved around and placed horizontally if desired. We will just leave it as it is for now. All the panels are tagged and have a very definitive purpose. We encourage our viewers to go through them one by one and understand their functionality. For this example, we are going to focus on these All Pins and Main Preview panels. In the All Pins panel, we can see the pins we have declared in our schematic design file automatically imported here. This happened when we ran the analysis and elaboration task from the Quartus Prime main interface. If we hadn't run the analysis and elaboration task, then we would have had to enter these pins manually. We find this auto import feature convenient, but it's always a good idea to review them one more time before proceeding. Now we are ready to assign the locations to our pins. This can be done in many different ways. The first way is to just double-click on the location field and scroll up and down to find the right pin number. The second way is to simply type in the pin number like this. The third and most convenient way is to just drag the node into the desired pin shown on the main preview panel like this. The main preview panel shows the 16 by 16 grid array of pins at the bottom of the FPGA device, similar to what we have created for our board block diagram. Now that we know how to assign the pin locations to the nodes, let's open the board block diagram that we created in our previous video titled Introducing Intel Cyclone and LP FPGA Evaluation Kit and find the right pin locations for our 50 MHz clock input pin and the LEDs present on the real board. The board block diagram can be downloaded in PDF format from our GitHub page. The link to the GitHub page is provided in the description below. Based on the board block diagram, we see that the 50 MHz clock input pin is located at E1. Let's just drag the node CLK50 to the E1 pin like this. Similarly, we can drag the other pins to the FPGA also. The user LED 0 is located at L14, user LED 1 is located at K15, user LED 2 is located at J14, and user LED 3 is located at J13. So let's just drag the nodes representing the pins to the associated pins on the FPGA. There is this neat little trick that can be used while dragging a bunch of similarly named nodes like the LEDs here by selecting all the nodes first and dragging them all together. We can drop them one by one on the grid like this. Everything else can be left as default for now. We will come back to them later in some other example project. Node properties can be viewed and changed by right-clicking on them and selecting Node Properties. This Node Property window opens in a super squeezed mode, so we will have to resize it for it to be usable. As we can see, this way we can change all the node properties from one unified interface. We can edit node properties of multiple nodes at once by selecting a bunch of them at the same time also. Now that we're done assigning pin locations to our nodes, let's just close this window and go back to our Quartus Prime main interface. All the pin planner settings have automatically been saved at this time. Talking about saving, we haven't saved our project for some time. It's always a good idea to save our project often. So let's save our project right now by clicking on the Save Project link in the File menu. In the Tasks panel, let's collapse the Analysis and Synthesis tab and double-click on it to actually run the Analysis and Synthesis task and see what error or warning messages we get and try to fix them before we move forward with the full compilation. Okay, so we did not get any warning this time. So let's move on to the next task, which is Filter, Place and Route, and run it by double-clicking on it. So this time we got some warnings. Let's review them and try to mitigate them one at a time. The first warning looks like it's related to a feature called Logic Lock, which is available only with a valid subscription license, which we do not have. So we will assume it as safe and ignore it. Now let's move on to the next warning. This warning states that some pins have incompatible I/O assignments. As we all know, in this example, we have 5 pins involved in this project and we assigned all the pins manually, so we will assume this warning has something to do with the JTAG pins present on our FPGA device and ignore it for now. The next warning looks like some kind of critical warning by the looks of the icon, so let's focus on that warning message and try to mitigate it right now. This warning message states that the Synopsys design constraint file was not found, and that this file is required by the TimeQuest timing analyzer to get proper timing constraints. Without it, the compiler will not properly optimize the design. So what is timing analysis and how does it affect our FPGA development process? FPGAs, by the nature of their complexity, are big in size and have many interconnected networks routed from end to end. So for example, if 2 clock signals start from one point and one signal goes out immediately to a signal pin and the other follows a more complex route and finally comes out of some other signal pin, then there is going to be a lag between those clock signals. This lag is due to the distance one of the clock signals had to traverse within the device itself. So to mitigate this inherent delay in clock signals and also between data signals, Intel's FPGAs have built-in programmable delays that can be configured to add delays to outgoing signals that are associated with each other. The TimeQuest timing analyzer tool is one such mechanism to analyze the timing delays between the clock and data signals and try to synchronize them at an early stage so that the final signals are all synchronized and usable. Timing analysis is in fact one of the final verification methods, but since it is so critical to FPGA development, Intel has decided to include this warning at an early stage to notify us, the developers, to incorporate the timing constraints from early on, so that in a later stage we will have mitigated most of the delays and have an easier time finishing up with timing analysis for verification. Now that we know what timing analysis is in general, let's create a Synopsys design constraints or an SDC file to add it to our project as the main timing constraints file. A new SDC file can be created by clicking on the new file link from the file menu and selecting the Synopsys design constraints file from under the other file sections. Now let's click OK and close the new file dialog. Now we will need to save this file with the same name as our top level entity file name, so that this file will be registered as our main timing constraint file and be included in the main compilation process automatically. If we choose to name it differently, then we will have to go back to the settings page and add that SDC file to be included in the project. Study of timing analysis and adding timing constraints to FPGA project is a vast subject and is probably the most important aspect of the verification process, which is what makes FPGA technology usable. Without it, FPGA technology becomes unusable due to the lack of synchronized clock and data signals. So we will dedicate separate videos for the study of timing analysis later. Since our design is not very complex and doesn't really require any timing analysis, let's just add some generic timing constraints to this project and get rid of the warning message from our compilation process. The timing constraints can be added by clicking on the Insert Constraint field present on the Edit menu. As we can see, there are many kinds of constraints that could be added to our design. Since all the timing related activities involves a clock, the first step in timing analysis is to create a clock for timing analysis. This can be done by selecting Create Clock from within Insert Constraint from the Edit menu. In the Create Clock dialog, we can give the name of the clock that we have given to our clock input pin. Since we are using a 50 MHz clock input, the time period of 50 MHz clock is 20 nanoseconds. So we will just enter 20 as period. Once again, we can enter CLK50 as our target, which is also the name of the clock pin in our schematic design. Now we can click Insert to finally insert the clock constraint into our Synopsys design constraint file. We should not forget to add a new line after every insertion to make room for the new constraints that will be added to our constraints file. Let's go back to Insert Constraint again and this time select Derive PLL Clocks to generate a constraint for the PLL clock that has been derived from our main input clock. In the Derive PLL Clocks dialog, we have to uncheck this Create Base Clock field and then click Insert to generate the constraint. Finally, we need to derive the clock uncertainty. This can be done by selecting the derived clock uncertainty from the Insert Constraint menu. Let's save the project once again and close the time constraint file. Now we are ready to run the full compilation process. We can do that by double-clicking the Compile Design task from the Tasks panel. This compilation is going to take some time depending upon the complexity of our design. Since our design is not too complex, it took about 30 seconds, which is shown here at the bottom right corner of the Quartus Prime's main interface. If we look at the messages, we will notice two warnings which we have already considered unavoidable, so we are good to go. Now let's briefly review the full compilation process and try to understand the steps involved. This can be done easily by expanding the tasks by clicking this arrow next to each task. The first task, that is Analysis and Synthesis, expands to Analysis and Elaboration, Partition Merge, and I/O Assignment Analysis. The second task is Fitting, which involves Place and Route. The third task is Assembly, which generates the final output programming files that will be loaded into our FPGA device. The fourth task is Time Quest Timing Analysis, which uses the Synopsys Design Constraint Timing Analysis file that we just created to generate a report. We will analyze the report sometime later. The fifth and final task is the EDA Netlist Writer. Since we did not use any EDA tool, this task was skipped, hence a question mark next to it. So that's all regarding the full compilation process. We will dig deeper as we move along with the course. At this point, we are ready to program the FPGA device by loading the output file into it by using the built-in programmer. In the webcam preview, we can see our Intel Cyclone and LP FPGA Evaluation Kit plugged in. It is currently running the factory default image, so we can see all 4 green user LEDs flashing. There are several different ways to open the programmer from the main interface. The first method is to click on this programmer icon present on the main toolbar. The second method is to click on the programmer link present in the Tools menu. The third and the most convenient way is to double-click on the program device task present in the task panel like this. In the programmer window, we can see this hardware setup button. Let's click on it and make sure that our hardware has been set up properly. In the hardware setup window that pops open, we can see our evaluation kit as listed as available hardware items. So we can assume our hardware has been set up properly and close this window. We also need to make sure that the mode has been set to JTAG. Now let's click this auto detect button and let the programmer detect our current configuration. In the select device window, we will need to select our device and click OK. In the pop-up window that follows, we will just click yes to let the programmer update its device list and overwrite any existing settings. As we can see, the device chain list shows 2 devices listed as device plugged into our computer, which is clearly not true. But if we look closer, it looks like the programmer has listed the JTAG programming interface, which is built into our board as the VTAB10 device, so we will just ignore it for now and load the output file into our device, which also happens to be the FPGA device present on our board. We can do that by simply clicking on either the chip preview itself or the file from the file list here. Then we will click on this Change File button, and in the Select New Programming File dialog that opens, we will browse into the Output Files folder and select this demo1.sof file and click Open. As we can see, the name of the file has been updated with our output file that we just chose. One last step before we start to program the chip is to select the Program/Configure checkbox, which will tell the programmer to actually program the chip. Once that is done, we can click this Start button and watch the progress bar to make sure the programming has actually begun. When the progress bar reaches 100%, we can see in our webcam preview that the LEDs start counting in binary, which is pretty cool. Now if we close the programmer window, it will ask us if we want to save the current settings. We will just say yes, so that we won't have to redo the settings every time we run the programmer. So that's it regarding creating, compiling, and programming a project using Quartus Prime Lite. Before we introduce the help system provided by Intel regarding Quartus Prime and the entire process of FPGA development, let's try to figure out what actually happened and look at many different perspectives this whole project can be looked at from. To do that, we can use a very simple locate node feature provided by Quartus Prime. For example, let's just select one of the output pins from the schematic editor and right-click on it. Then we will click on the locate node link. This will list 7 unique perspectives this node can be looked at from. They are locate in assignment editor, locate in pin planner, locate in chip planner, locate in resource property editor, locate in RTL viewer, locate in technology map viewer, locate in design file. Right now we are viewing the node in design file. That's why the locate in design file selection has been grayed out. So let's look at this node from these different perspectives one by one and gain a much deeper appreciation of the FPGA device and the design process as a whole. Let's select the locate in assignment editor first and see what it has to offer. If we uncheck this filter on node names, then we will see all the nodes being used by our design listed with their various assignments, like assignment name, value, and their status. This assignment editor will play a very important role when we start working with more complex designs. Keeping that in mind, let's close it for now and move on to the second perspective, that is locate in pin planner. This is the same window that we use to assign pin locations to our nodes. Since we have already used this tool, let's close this window and move on to the next perspective, that is locate in chip planner. In the chip planner, we can see where in the FPGA die is our node located at. It also shows all the logic elements being used by our design. If we select the zoom tool from the toolbar located at the right of the screen and right-click several times, we can have a bird's eye view of the FPGA device. Now if we select the selection tool that looks like a mouse cursor and select the whole FPGA device like this and click on the expand connections icon, then we'll be able to visualize actual connections between the nodes being used by our design elements. This tool allows us to follow our signals through the actual device and find bugs and mitigate the shortcomings in our design. Let's close this window for now and move on to the next perspective, that is locate in resource property editor. In the resource property editor, we get an even more in-depth look at our element. Here we can see the actual gate level implementation of our design. For example, here we can see how an output pin signal is connected to the pad that goes after the pin present on the FPGA device. We will come back to this resource property editor when we study how the logic elements are implemented in an FPGA device. For now, let's close this window and move on to the next perspective, that is locate in RTL viewer. In the RTL viewer, we can have a look at our design from a textbook perspective. This is showing how our designs would translate at a symbol level. But here we have the capability of digging deeper into our modules to look how those components are implemented at a gate level. For example, if we click this plus symbol on this counter and keep going deeper and deeper, we will see how each bit is implemented within this counter at a gate level. We will use this tool later when we study Verilog to translate our Verilog code into designs and vice versa. For now, let's close this window and move on to the next perspective, that is locate in technology map viewer. The technology map viewer shows the actual netlist view of our design implementation. This is what gets loaded into our FPGA when we program the chip, of course in some binary stream format. So this can be considered as our final perspective before it gets loaded into the FPGA. We can close this window for now and get back to the Quartus Prime Lite's main interface. So that's it regarding the 7 unique perspectives of our design for now. We will explore each and every tool in detail sometime later. In this video, we just wanted to give a taste of what's out there and how awesome Quartus Prime software's features really are. Now let's look into the Quartus Prime help system built into the Quartus Prime software itself. If we click on the help menu, we will see this help topics listed as the first item. Let's click on it to see what it has to offer. It will open up a new web page with non-exhaustive help topics. We recommend our viewers to go through it briefly and make sure they know where to look when they need them. We will also be using this resource to provide up-to-date relevant information to our viewers. Help menu also includes several other important links like tips and tricks, which can be used as a reference to customize our interface, use tools more efficiently, and optimize our designs. Another really important link present on the help menu is the on the web category. Here we can find links to Intel's official help resources present on the web. These web pages are constantly being updated to keep the information they provide relevant and up to date. The training link provided within this On the Web category takes us to Intel's official training website. Here we can find links to instructor-led trainings, online trainings, and virtual classroom training resources provided by Intel and its partners. Finally, what we consider the ultimate resource is the Quartus Prime Handbook. It can be found by clicking on the Quartus Prime Handbook link from within the On the Web category. It is the most up-to-date reference we can find on the internet. The PDF version of this handbook is about 2,200 pages of goodness. We highly recommend our viewers to download this handbook and use it alongside this course to master the Quartus Prime software suite. Saying that, we have reached the end of this video. In the next video, we will focus solely on the Intel Cyclone 10 LP FPGA device and dig deeper into its core fabric. We will see how the logic elements are implemented and how the interconnects work. We will also look into the memory modules present within the device, and finally we'll see how the clock networks run through the device. We will then combine our overall understanding of this device with the perspectives provided by the Quartus Prime software. That way we will be able to understand the limitations of our device and the FPGA technology before diving into the magnificent projects that we'll be building using this technology later in this course. We hope our viewers found this video helpful. If any comments, don't hesitate to leave them below. So long for now.